You saw in the last video that any comparison-based sorting algorithm will have, in the worst case, at least an n-log n runtime. So if we want to do any better than that, we can't use comparisons to find the total order of elements. We need some other way to sort elements without actually comparing them. So to obtain a linear time sorting algorithm, we have to be more restrictive about the type of input that we're sorting in order to actually guarantee that we can sort it in linear time. So the linear time sorting algorithms you'll see here don't work on just any input. In order to avoid using any comparisons, we're going to assume that the keys we're sorting by are very specifically integers, and here, that they're integers and they're within the range of 0 to r minus 1. Now you might see if you're comparing against in your book, they use capital N. I'm going to use r here just because we also have little n elements. So to avoid any confusion there, I just have r as our maximum. So this means that any of the elements we're sorting, note that the elements themselves can be complex objects with multiple attributes associated with them, but the key by which we're sorting those elements must be an integer, and it must be within the range of the smallest value it can have is 0, and the largest value that it can have is r minus 1. Now, if we meet these requirements, then in order to beat this runtime and get something which is faster than n log n, we can't use comparisons. So we need some other way of sorting items without comparing them. And in doing so, we can sort in linear time, provided that this upper bound on our integers r is small enough. And what do I mean by small enough? It kind of depends. We're going to see a few different approaches which handle increasing r values and can still sort in linear time. The first one that we're going to talk about is bucket sort. Bucket sort works by creating a separate array of size capital R, and it uses each cell in the array as a bucket, essentially. So then our sorting occurs in two phases. First, we scan through our original sequence, and one by one we place each item with key k in the bucket at index k. So we have some sequence here of unsorted elements, and then we create an array, let's call it B, and how large this array is going to be based on the maximum range, this maximum integer value that we could possibly have. So this will be going from 0 all the way up until the last index will be r minus 1. So our sequence has some numbers in it, some elements with integer keys, but all of those integer keys are within the range of 0 and r minus 1. So maybe we have 5 and then some object associated with it. 5 is just the key associated with that object, and some other values, r minus 1, b, and so forth. So these are the unsorted elements that we have. Bucket sort's first step is create this array, this large array of size r. And then in the first phase of bucket sort, we're going to take every item from our unsorted sequence and just one by one, starting with the first one and working our way to the end, removing this item and then placing it at the index associated with this key. So the key is 5, which means we're going to place it at index 5, this entire item. So not just 5, but also the item associated with 5. So we'll have here the element 5a. And then we move to the next one. This has key r minus 1, so we're going to place this object in bucket r minus 1. And we go through one by one and do this for every element in our sequence. So this is the first step of bucket sort. This is what we have here in our while loop. For every item in our unsorted sequence S, until we've gone through every item, until this is empty, we're going to take whichever that first item in the sequence is, so we can remove the first item in a sequence in constant time. So here's the key and the object associated with that key. And we'll insert at this index k into our array this key element pair, but we're going to insert it at the end of this. So each cell is a bucket, meaning we're actually storing a list at each cell, because we could have we could have multiple elements that have the same key. So we'll be able to store multiple items at each cell. So this is why we're going to call them a bucket. So we insert at the end of the list, which is stored at key K of our bucket. So this is the first phase of bucket sort. Just take everything from the sequence and dump it into its appropriate index in this larger array B of size R. Now the total runtime, so we haven't finished yet, but the total runtime of just this while loop is linear with respect to n. This is because we have n elements in our sequence, and we can do these operations in constant time. Remove from a sequence, access the first element, access an index in an array, insert at the end of a list. So the total runtime of just this first while loop, the total runtime of this first phase of our algorithm, is big O of n. So now let's see what we do in the second phase here. We go through each cell of this larger array B, so from 0 all the way up until the end, r minus 1, and we're going to check to see, is there anything stored at that cell? So for example, just with this small sequence, we never stored anything here. We don't know that yet until we're finished, so we're going to check every cell of this array and check to see, is there anything stored at that cell? If there is anything stored at that cell, then we're going to take whatever is at the beginning of it and put it back into our sequence. So when we're done with the first phase of our array, we've removed everything from our sequence, so it's empty. We've put it all into our array. Now we're going to go through in the second phase and take every item from the array and put it back into the sequence in a sorted order. So if there's something left in this bucket to take, we're going to remove whatever the first one is. Maybe there's multiple items, so we'll kind of take them one by one. Remove the first item from that bucket, and then insert it into the end of our sequence. So this will give us an ascending order of elements. So how long would this next one take? This is a little deceiving because it looks like, well, there's a for loop and then a nested while loop, so it looks like maybe it could be quadratic, but this would not be an appropriate analysis here. So our first for loop, definitely this goes from 0 to r minus 1. So the total runtime of our for loop is big O of r, because we have to go through each cell. We've got r cells to go through. But we don't always go through this while loop. We're only going to go through our while loop. We're going to evaluate this condition r times to check to see if it's empty, but sometimes it will be empty, so we won't execute these 2 lines of code. So how many times will this not be empty? This is based on how many items we had in our original sequence, because we'll have some cells in this array that are empty that we're not storing anything at. So we're going to check them to make sure that they are empty, but if they're empty, we're going to move on and we're not going to do anything else at that cell. And we'll also have some cells that maybe are storing multiple items, all that have the same key. And so for them, we're going to stay at them longer and we'll execute these lines of code for each element that we have stored there. So the total number of times that we're going to execute these 2 lines of code here is based on however many items we had, because here we're removing an item from the array that we had inserted, and we had only inserted n items. So the total number of times that we're going to execute these 2 lines of code is big O of n. We're not going to do this r times, or r times n times, but the total number of times we'll call these 2 lines is big O of n. So that means our total running time for this second phase is big O of n. This is how much time we spent removing those items from the array and putting them back into our sequence, because we can access an array in constant time, remove from a list in constant time, insert into the end of a sequence in constant time, and we're doing this n times. So this portion costs n, and then we're going to go through our for loop r times, which means we're going to evaluate this condition r times. So even though we only execute these lines of code a total of n times, we still have to check to see, is there anything at the cell? So our total runtime here for the second phase is big O of n plus r. So main idea behind bucket sort: first, we scan through the original sequence and one by one place each item with key k into the bucket at index k. And then we scan through the array from index 0 to r minus 1, and one by one take all elements in that bucket and put it into the end of our now sorted sequence. So our total running time now is big O of little n plus r. Now remember, r is the range of integers that we have. N is the number of items that we have. R is the maximum value that some integer could take, one of the keys that we're sorting by. So when would this be linear time? When would this be big O of n? This is when the range of items that we have is big O of n. So if we're sorting integers, but the integers are no larger than n, or 2n, or 3n, all of that is still big O of n, it's linear, then our total running time is big O of n plus r. If r is big O of n, then we're left with, then our runtime is big O of n plus, if r is big O of n, this is also n, which is linear still, since we end up dropping that constant coefficient. Okay, so this is one example of if we have integers that we're working with, this is what we're sorting by, the keys that we're sorting by, and those integers are in the range of 0 to r, then bucket sort will run in big O of n plus r time. If we know that the range of those integers is linear, that is no more than some constant number times n, that's the maximum value that an integer could take, then we can sort in linear time. So that's pretty restrictive as to what the type of input that we're sorting is. Okay, so let's see an example here. Let's say we're given this sequence, which is unsorted, although we know that the keys we're going to sort by here are integers, and they're within a particular range. So how do we know the range? This could be one of two things. Maybe we know ahead of time, based on the type of data that we're sorting, maybe we're sorting by age or by rating. So without even looking at the data, we can say, okay, this is somewhere between the range of 0 and some number. If this is, maybe we're rating from 1 to 10, then we know the maximum number would be 10, or so forth. So we might know ahead of time already what the range would be. But if we don't, then just as a pre-processing step, we can always scan through the entire sequence in total linear time, just before we do anything, before we sort, and find whatever the maximum number is, and then that would give us our maximum range. So let's say we knew ahead of time, just because maybe this is a rating system or some other thing, let's say we already knew that our keys would be in the range of 0 to 9. So maybe we don't have anything exactly 0 or exactly 9, but we know it won't be larger than that. And we're given this unsorted sequence here. So in the first phase of bucket sort, we're going to check for this item what its key is, which is 7, which means we're going to place that item at index 7 in our array. So we create an array from 0 to 9, knowing that our keys will be no larger than 9. So our first step here is we place this item at index 7, just at the first spot in this list, and then we move to the next one. So we'll place this item at index 1, we'll place the next item at index 3, we'll place the next item at index 7. We've already got something there at index 7, so we're just going to add it to the end of that list. And then another item at index 3, we'll place it at the end of that list, and then the last one we put at the end of the list at index 7. So in the first phase, we form this array B. And in the second phase of bucket sort, we're going to go through each cell of B and output, kind of take all of the items that we had there and place it into our now sorted sequence. So first we go to index 0, there's nothing there, so now we go to index 1, and we'll remove everything from this cell, which is just 1C. Then we go to index 2, and there's nothing, index 3, and we're going to start kind of from the beginning to the end here. So first we'll take 3A and then 3B. And then we go to index 4, 5, and 6, but there's nothing there for us to process. We still have to check to make sure that there isn't anything there. Then we move to index 7, and we'll, one by one, from the beginning to the end, take all of these elements and add them to the end of our now sorted sequence until we've gone through the entire array that we had created. So now we have a sorted sequence. And note that at no point in time did we actually compare one item to another item. We know that if we're using comparisons in order to sort, this was in the last video, then we would have to have n log n comparisons in the worst case. But we didn't use comparisons here, and this is how we're able to kind of get around that lower bound, is we don't have a comparison-based sort. We're using the fact that the keys we're sorting by are integers, and then we can use those integers to index into an array, which we can do in constant time. And then it's just a matter of how many times we do that. So we can, bucket sort is also useful to create visualizations like a histogram. So for example, we could use it to plot student scores on an exam by mapping each grade to an integer. And then we could create a large array to store student exam scores. And then a student's exam would be added to the bucket corresponding with the letter that they received on their exam. So then the size of each bucket gives us already the frequency of each letter grade, which gives us a kind of a nice visualization to show the distribution of scores. But this is scores for an English exam. So I am hopeful, because you're all very smart students, that for your upcoming algorithms exam this will be skewed a little bit. We'll have more over on the right side here. All right, now what are some of the key properties we have for bucket sort? We know that we can only use bucket sort if our keys are integers, and specifically each key k has to be in the range of 0 to the largest it could be is r minus 1, because we're going to use that key as an index to place it into one of these cells into an array. So they can't just be arbitrary objects, they have to be integers. The keys have to be integers in this range. But in doing so, we don't use any external comparator, we're just using indices here. And this is a stable sorting algorithm, because as we place items into our larger array in order to sort them, we maintain that if we had, let's say, an item, let's say 0A and 0B, and this is exactly the order that we had encountered them in our original sequence, we'll add them in the same order to index 0. First we'll add A, then we'll add B, and then when we remove them, again, we kind of process them in that order. So this is a stable sort, meaning that we preserve the original order of items when those items have the same value. But we can extend bucket sort also to handle the case that the keys that we have aren't integers. Maybe we have, or they're not in the range of 0 to some number. Maybe they're in a different range. So we have keys that are integers, but they're in the range from A to B. So maybe it's from, 500 to 600. Well, we can always offset all of those keys by whatever that minimum value is. So even if we had negative keys, for example, we can offset them so that they always start at 0 and then end at some number. We could also adapt this in order to use, even if we didn't have integers, if we had maybe string keys, but we had a constant number of those keys, maybe those are our states, for example, then we can essentially map each key that we have, which isn't an integer, map it to some unique integer within the range of 0 to some number, and use bucket sort that way as well. Okay, so this is the main idea behind bucket sort. If we have keys within this range, then we can use bucket sort to sort all of those elements in total n plus r time. This is linear if r, the range of those keys, is linear. We're going to see another example of a linear time sorting algorithm in the next video called radix sort.